So welcome to our video session for today. So let us have additional problems on simple stress that would involve normal stress, shearing stress, and bearing stress. So we have here a 21.88 millimeter diameter bolt having a diameter at the root of the threads of 18.25 millimeter is used to fasten two timbers together as shown. The nut is tightened to cause a tensile stress of 24 megapascal in the bolt. Compute the shearing stress in the head of the bolt and in the threads. Also, determine the outside diameter of the washers if their inside diameter is 28.13 millimeters. The bearing stress is limited to 1.24 megapascal. So in this setup alone, this will involve three types of simple stress. Namely, first we have the normal stress on the bolt, the shear stress on the head of the bolt, and the shear stress on the root of the threads within the nut, and the bearing stresses on those washers. So if we take a quick review on those stresses, first for the normal stress, when this nut is being tightened, of course, this will induce your bolt shaft into a tensile mode. It will tend to stretch this one because as we tighten this one, this is being stretched. And then for the shear stress, of course, the shear stress is a cutting force which is tangential to the section. So if we take a look at the head of the bolt, if this is in stretch mode, say this is the head, there will be shear forces surrounding the perimeter wherein the shaft is attached to the head because it is actually pulling this, causing a hole in it. And the hole is caused by your shear force or the tangential force that is within the perimeter of your head of the bolt. And as for the shear stress within this portion or within the nut, there lies the threads which is actually interlocked with the threads also of your nut, and therefore if this is being pulled downwards, there will be a tangential force surrounding the root of the threads. So therefore, these are shear forces as a result of pull due to tightening of this nut. Okay, so there will be shear stress and normal stress. How about the bearing stress? So recall that bearing stress is a contact stress, or actually it is a contact pressure between two surfaces wherein this washer is actually in contact with the timber and the root of and the head of the bolt, and this lower washer here is in contact with the timber and the nut as well. So therefore we have the bearing stress. So working with the unknowns, say for letter A, we have the shear stress in the head of the bolt. We simply use this formula. So on this formula, we know that V is also P, okay? Because V is caused by the pull P. And in the problem, we do not know yet the value of that force. And that force can be derived from the given tensile stress on the bolt. Okay, tensile stress is actually a simple stress or normal stress in the bolt. Now, since we know this, we can now determine the value of P, wherein P is also the shear in the head of the bolt, or the shear force in the head of the bolt. So before we can work with this one, we first determine our P by using the normal stress formula, and this is tensile. Okay, by using this, we have 24 megapascals. This is equal to the unknown P, and then the area, of course, we'll just use the cross-sectional area of this bolt shaft, and it has a diameter of 21.88 millimeters. So we'll just write the area, that is pi all over 4 times 21.88, and this is squared. So by that, we can say that P is equal to 9023.93 Newton. Thus, this is also equal to the shear force within the perimeter of the head of the bolt. So, moving on with the first unknown, we can now determine this by simply equating it to 9023.93 all over the shear area. So this time, what is the shear area? It is the perimeter of the circular portion times the thickness of the head of the bolt, which is 12.5 millimeter. So the perimeter of a circle is actually a circumference, and that could be expressed in pi times d. So pi, the diameter is 21.88, okay, that is the perimeter, times the thickness, and the thickness is, here we have 12.5 millimeters. So by cross multiplication, by division, the shear stress in the head of the bolt would equate to 32.99 megapascal, which is actually the first unknown in the problem. So moving on to the other required, we have the shearing stress in the threads. Say, let us have the shear stress in the threads. We employ the same formula. Tau is equal to V over A, and then we use the same force, shear force, all over the shear area. The shear stress within the nut is the root of the threads. So here we're going to use 18.25. So again, we use the perimeter, pi d. So the diameter is 18.25. By the way, 18.25 is the diameter on the root of the thread times 15.63 millimeter, or the thickness of the bolt or the nut itself. So here we have 10.08 megapascal. So it is the second unknown in the problem. And then finally, for the third requirement of this problem, we need to determine the outside diameter of the washers if their inside diameter is 28.13 millimeter. So the bearing stress is limited to 1.24 megapascal. So say, let us have letter C for that. Say letter C, the outside diameter of the washers so I'll just denote it to be DO. So of course, the washer is a donut shape wherein under the conditions of the problem, we know the inside diameter equivalent to 28.13, and this is the unknown outside diameter. It is simply equal to the area of the larger circle less the smaller circle, so that we can come up with this shaded portion here, or actually the cross-sectional area of this washer, which is actually the contact area or the bearing area. So we know the formula. This is equal to simple formula. Okay. Bearing stress is equal to bearing force over the bearing area. So the bearing stress, I think it is given the problem, equivalent to 1.24 megapascal. So we'll just have to place it on the equation, and the bearing force is actually this one. So 9023.93. Okay, so the bearing area, the area of the smaller or the larger circle, so pi over 4 times dO squared. So we'll just have to deduct the area of your smaller one. So in terms of diameter, we'll just have to factor out pi over 4 and then just have the difference of the squares of the diameters. So we see here that we have a single unknown equivalent to dO, and by cross multiplication and manipulation, so this will yield to a square root, and then extracting the square root, we have 100.29 millimeters. So this completes this the solution of this particular problem. Okay, so moving on, say we have another problem, and this problem is actually the problem of the shearing stress. Since we have here a joint section, this is joined through a weld connection. So remember that the shear stress is taken or is occurring on sections with a joint, okay, with joinings. Okay, so the principle in here is there will be a notch between these members so as to facilitate connection here, and this notch is a V-shaped notch. Each of the diagonals are inclined with 48 degrees. So we're going to determine the shear stress on the welded section. So let us have the free body diagram first. Say here we'll just consider the cut portion, considering the left portion. And of course, on that left portion, there will be a tensile orientation of this. Say we have here P. Okay. As a counter, the internal force on this will be a P here, the same P here, but it will just be distributed on the surface of these joinings. Say we have here P tangentials. And this P tangential is just a component of your P. Perhaps we can indicate that into another color, just to distinguish that P here is the mother force, and the P tangential is just the component of that mother force. And of course, there are two normal forces here that are perpendicular to your tangential forces. So those are perpendicular to your tangential forces, but we are not so concerned with these normal forces, but our concern is to determine the tangential force, because the tangential force is actually the shear force. Now it is noted that this tangential force is inclined at 48 degrees with the horizontal, and there are two of them, two tangential forces here, which is considered as the shear force on the cut portion, okay, that is oppositely directed against the tangential component of P. So therefore, if this is 100, so the resisting force here, since it is shared by these two surfaces here, so instead of 100, we can just have the resisting force here to be equal to P over 2, or that is equal to 50. So this 50 will be our basis in determining the tangential component of your P, which is 50 kilonewton. And I think we have here a right triangle relating the right triangle to your mother force. Okay, say this is the perpendicular angle. This is 48 degrees. This is your shear, okay, which is P tangential. And this is 50 by function of cosine 48. Adjacent to your 48 is V all over 50. Therefore, V here is 50 cosine of 48 degrees. Thus, this is equal to 33.46 kilonewton. Okay. Now that we have derived this, we will now determine what is the shear area. See, I'll just have to shade this area here. Okay. And that area is derived by having, I'll just denote this to be Z. Okay. For that Z, we'll just have to consider a right triangle say this is dimension Z. This is 48 degrees. Okay, so this is 50 millimeters, as we can see in the problem. So that inclined area is equal to the shearing area, which is equal to Z times 100. Okay, so we can derive Z by function of sine. Okay, sine 48 degrees is equal to opposite to your 48 is 50 divided by hypotenuse Z. Thus Z is equal to 50 all over sine 48 degrees. So this will be now substituted here. Say 50 all over sine 48 times 100, and the shear area will be equal to 6,728.16 square millimeter. So by this, we can now finally determine the shear stress on the welded section. So this is V all over A. So we have 33.46. This is in kilonewton, so we multiply that by 1000 divided by the shear area. So finally we have shear area, the shear stress is equal to 4.97 megapascal. Okay, so I think we are done with this problem, so stand by for the next section, so video lecture. So thank you for listening.